Good afternoon and welcome to our hospital renovation project presented by the Earthquake Engineering Research Institution student chapter. My name is Jennifer De Avila. I am the president/team captain this current year. And here I have Debbie Altamirano, my vice president, who will present the rest of our team members.
Good afternoon, everyone. Presenting with us today is also Vanessa Fernandez, Isis Argueta, Jared Abeg, and then we also have so highlighted here a few of our other teammates that were not able to present with us today. So on today's agenda, we will go over the request for proposal, the geotechnical findings, the architectural research, and the structural findings for this project. So let's paint a picture. The scene is year 2020 in Seattle, Washington. The mayor of Seattle has made a plea to acquire urgent funds for increasing hospital space to catch up with the healthcare demands of rising COVID-19 cases. In the addition of constructing of a new hospital building, an existing hospital of the greater Seattle area was selected for a structural addition. And this is what we will be presenting today. So for the geotechnical, Washington State has one of the second highest risks for earthquakes due to its geological location. Washington has a Cascade Range and a huge mountain range that extends through Washington and is part of the Ring of Fire, and that is infamous for its volcanic eruptions and earthquake activity. These mountains are all within the same Cascadia Subduction Zone, which is a type of convergent plate boundary formed as a result of the Juan de Fuca plate subducting beneath the edge of North America. Because of this, it has a lot of pressure buildup, which makes this area prone to major earthquakes. We also have three faults in this area. We have the Seattle Fault, the Devil's Mountain Fault, and the Tacoma Fault. The Seattle Fault and the Devil's Mountain Fault are two of the most active faults in the area. They are both prone and capable of a magnitude of 7 earthquake, and they are both within less than 30 miles of our proposed hospital building. So this creates an issue. Because of its geological location, some consequences of the earthquakes in this region are tsunamis, landslides, and liquefaction. Due to its potential of liquefaction and rupture of the local faults, we must carefully analyze and interpret the subsurface soils. So there is a water table about 10 feet below the ground surface. And then within the first layer, the first 0 to 55 feet is sand. As we explore further, we realize that the soils in this area have a water content ranging from 0 to 20% saturation. As you look deeper within the 55 and 85 feet, the soil is still sandy and gravelly, but the density shifts. So now it's a more medium and very high dense soil. As we get lower in the 89 through 96 feet, we have sandy, gravel, and gray silt. So the silt is very soft and still wet. So for the next 3 feet, it's still prone to liquefaction. Next slide, please. Thank you. So as we identify the ranges and try to classify and see what class this falls under, we use the PI index of less than 4 to meet the criteria of ASCE 7-16. So for the site soil class, therefore, it fell into the class F. But based off of the PS suspension log, the shear wave velocity for the first 30 meters is 30 to 613 feet per second. A shear wave velocity ranging in the 600s corresponds to site class D. So the design response spectrum is derived from the code and it is a site-specific earthquake scaling tool. In doing so, we find that the spectral acceleration of the existing structure and the existing structure plus its addition is 0.5869 grams and 0.2934 grams respectively.
Next, we have to select a ground motion. We use a seismic degradation hazard specific to our site to estimate the seismic activity. We chose the period of 2 seconds and found the magnitude mean that the fault contributed, which is 6.95. And based off of that CSZ interface zone that we spoke about, we can predict a magnitude of 9.02. So this information helps us narrow down the ground motion selection. So once we have narrowed down our earthquake search, we used the site's shear wave velocity, rupture mechanism, rupture distance to narrow down our search. We've also scaled one of our selected earthquakes to match the design response spectrum. And we chose this specific earthquake in the brown box because it was close in magnitude from the nearby faults, and it also matched the shear velocity of our site. Next, we will go over the architectural portion of our site.
Hi, good afternoon, everyone. So for this project, we wanted to do some research about the architecture around the city of Seattle. We found that modern architecture in Seattle is largely based on the use of geometric shapes, asymmetry, and an abundance of windows. These elements give the building its unique yet functional aesthetic that fits into the modern city setting. So on this slide, we have two examples of this. We have the Grand Central Library, as well as the F5 Tower in downtown Seattle. Both of these buildings show various uneven shapes, asymmetry, and a large use of glass for their windows. Next slide. So for our own design, we wanted to take some inspiration and incorporate some of these elements. For example, our addition features a slanted design covered in all glass windows. Our east and west elevations feature triangular windows. Our north and south elevations feature rectangular windows, but they're laid out in an asymmetrical pattern. We decided to incorporate these triangular windows on the east and west elevations to allow for the bracing in the structural design of the building in the addition. And we also wanted to incorporate a lot of windows to allow for natural lighting.
Hi everyone, my name is Vanessa and I had the opportunity to create the floor plan for our hospital design. On the right side, you can see our AutoCAD drawing of this floor plan where 12 rooms are shown, including the exam room for patients, waiting rooms, supply rooms, accessible restrooms inclusive to everyone regardless of gender or disability, the nursing station, doctor's office, staff lounge, and lastly, a vending area where people are allowed to eat and drink. The total number of rooms we were able to add due to the addition was 84. The amount decreased as we moved up each floor since the design of our addition has our square footage decreasing from 2,250 to 1,125 square feet. And moving on to the next slide, please. So this further displays the decrease in area of each floor once we hit floor 12 up until the roof. The additional 11th floor still has the same area of the first 10 existing floors, so it's still able to hold 12 rooms. On the further right, we tabulated the square footage for each room as well. And the biggest room in the hospital is the supply room, which is typically narrow and where clean linen may be put away, as well as the medical supplies that include catheters or surgical masks. It has 2 entryways so that workers may enter from either side of the building. And the smallest room, on the other hand, would be the patient rooms and the restroom, due to the fact that it is essentially made to hold 1 person at a time. The patient room, of course, can have 2 people. That will typically be the patient and the examiner, but it also accounts for any possible guests that come with the patient. And overall, with designing this floor plan, the goal was to make everything easily accessible for everyone while still maintaining the sleek and modern facade of Seattle.
Thank you, Vanessa. In addition to the space planning, LEED certification was also pursued. Within the LEED certification, there is a category for healthcare. This was aggressively pursued. Here is our healthcare checklist. Our our project was able to earn 87 points, which led us into the 80 to 110 range for a LEED Platinum certification. Moving into the structural component of our project, we were given design construction plans for the existing hospital. And typically in a physical non-COVID setting, we would construct a balsa wood tower physically and place it on a shake table to determine our deflections. With this new challenge, we were tasked to create a SAP 2000 model, also still within the balsa wood material, and perform the time history analysis within the software. We were tasked to determine how the existing software will perform under the seismic activity and geotechnical conditions.
Hey, everybody, I'm back. So this here is just the time histories that they provided to us. We plotted them with acceleration on the y-axis and then time, of course, on the x-axis. Basically, this just summarizes, we had different time steps for the time histories. So we had to like take that into consideration when we're plugging it into the software. And then also they have different lengths, as you can see. Note TH4 there on the bottom right. That one actually produces the largest base shear in the structure. Next slide, please. So one of the metrics that we were supposed to look at for this deliverable, the structural deliverable, was the inter-story drift ratio. So basically, it's just if you take two successive floors, like the top one and the one below it, calculate the drift at that story level, and then normalize it by the height between those two floors. Next slide, please. And then here's just an excerpt from ASCE 716 showing the allowable story drift for risk category 4, which is what our structure is since it's a hospital. It's going to be 0.01 times the height below that particular level.
Here is our existing structure modeled in SAP 2000. Overall, our inter-story drift ratios and the X direction were within the allowable range. Although in the Y direction, it was significantly larger. And here are our base shear results. With our existing structure, the time history 3 actually produced the largest base shear results.
Okay, so these are the results for our addition once we had modeled it. So initially when we had the inter-story drift ratio, and we're just trying to figure out, like what is this good for? It became pretty clear once we had plotted it against height for the addition, because we terminated the bracing on the westerly side of the building there, you can see where the arrow's pointing. And once we plotted the IDR versus height, you can see like a discontinuity in the overall trend. So it's pretty good at showing you where you might need more bracing, anything like that. Next slide, please. So this table here just summarizes our base shear results for the addition. And this is what I was talking about. Sorry, Jen, I didn't mean to say for the whole entire structure, but for the addition, time history 4 did produce the largest base shear.
Team, you're at time, so you can wrap it up, please.
Okay, yeah, this is just our attempt to check the interactions. SAP 2000 didn't allow us to check graphically like most design checks that are out there in FEM software for wood, just because this was a balsa wood structure. So we did attempt to check the interactions in a tabular format.
In conclusion, most of our goals were achieved. Our safety, our IDRs were significantly less than the allowable range. Our expansion, we doubled the original square footage, allowing for 84 extra patient rooms. And we also were in alignment with the City of Seattle's sustainability goals in achieving a LEED Platinum certification. Here are our resources, lots of them. And thank you. And now we'll open the floor for questions.
Well, actually, the judges get to ask questions first. Thank you, team. Any questions from the judges first?
Yes, I have a question regarding your base shear. You're using a fault line which is close to the building, right? to get your base shear, but this is a tall building. So did you consider looking into the long period, or how did you get that base shear?
So sorry, the base shear was actually output from SAP since we're doing time history analysis.
Mm-hmm.
So
So did you consider, tall building in the long period for that analysis to get that base shear, or is it because you're actually putting in the ground motion, right, into the?
yeah, we're putting in the ground motion.
Okay.
We did do an analysis using the design response spectrum, but that was our next step in getting the periods and comparing it against it as well.
No
Yeah.
problem. Yeah, because you're using a very close fault for a tall building. That's more for a short period, but taller building, you have to look at the long period and kind of see if you do get the right base shear.
Yeah, there's so many aspects to explore, but they really wanted us to look at the floor ratios more for the equipment on the hospital.
Okay.
So, yeah.
So I have a question in regards to consideration of when you're doing this addition on an existing building, were there impacted areas, and how did that impact the facility in terms of schedule and costing? I guess that wasn't part of your exercise, but just something to think about when you do something like this, especially on a hospital. That's a huge major cost factor in consideration. There could be hazardous materials that you're interfering with, like asbestos and such. So just wanted to know if there was any thought on that.
I think our main consideration was retrofitting and seeing where the current existing structure kind of needs a little strengthening in. But definitely, I know LEED would want us to take a look at the chemicals within the material itself as well. So that is a next step. Thank you.
I have a question.
Yes.
The seismic history of the site. What is the seismic record? Do we have large earthquakes? Have they been recent? Has there been a review of that by geologists? So we have a history of a 9.0 earthquake or an 8.0, even.
Mm-hmm. That 9.0 magnitude, geologists have looked into it, and I think it's within 50 to 90 years. That's their estimation. So it's definitely a target that I think we should consider during the structural analysis.
Past evidence of an earthquake of that magnitude.
I think more along the edge of the coast near that Cascadia Subduction Zone that was mentioned in the beginning. Okay. And it also led to the tsunamis, which was why there was so much consideration into liquefaction.
Thank you.
All right, thank you. Hospital renovation, since we only have about a minute for our next team, I'm gonna stop the questions. Thank you.